If you opened up an old CRT TV, you would see its large rear section was the cathode ray tube. Electromagnetic coils surrounded the tube's neck, with a precision electron gun installed at the rear. This gun emitted focused electron streams, acting as the negative cathode terminal. The front display screen served as the positive anode. The entire tube was coated in matte black paint to prevent stray light reflection. The inner screen surface was covered with phosphor powder. When high-speed electrons hit the phosphor layer, it instantly lit up and glowed brightly. The screen consisted of millions of tiny pixels, yet a single electron gun only lit one dot at a time. Only one pixel illuminated at any given moment, which seemed impossible for forming complete images. The solution relied on the same core principle: extreme speed. Speed was the key breakthrough. The electron gun scanned at an ultra-high frequency, far too fast for human eyes to track its movement. It shifted positions thousands of times per second, adjusting coordinates within microseconds. Due to visual persistence, our eyes perceived these rapid dots as a unified whole. With a fast refresh rate, smooth, continuous video appeared on screen. Still, audiences craved more than monochrome pictures. Black and white displays could no longer satisfy demand. The race to create practical color television began. American electronics giant RCA solved this challenge. They used special prisms to split incoming light, separating scenes into red, green, and blue light beams. Each color channel fed into an independent dedicated CRT tube, with every tube processing one primary color and generating its own exclusive signal. On the receiving television end, 3 separate CRT monitors received the individual color signals. Precision lens arrays then combined the 3 projected images onto one screen. Unfortunately, this design required 3 full CRT sets, tripling manufacturing costs overnight. Additionally, its unique triple color signal format was completely incompatible with existing black and white TVs. To fix these critical flaws, RCA engineers developed an optimized solution, integrating 3 electron guns into a single CRT housing, scanning the screen simultaneously in sync. The display screen underwent specialized coating, covered with countless microscopic clusters of phosphor dots. These phosphors came in red, green, and blue variants, with one trio forming a single full-color pixel. These pixel clusters covered the entire display. When electron beams struck each phosphor trio, light brightness varied by beam intensity. Through this method, engineers controlled the color output of every single pixel, viewed from a normal viewing distance. Individual colored dots blended seamlessly together, forming vivid, lifelike full-color imagery. One major challenge remained: the microscopic size of each pixel cluster. How could electron beams accurately target tiny color pixels? The fix was simple yet ingenious. A shadow mask installed directly behind the screen glass. This metal plate featured precision tiny holes, perfectly aligned with every individual pixel cluster. As electron beams traveled forward, they only passed through matched mask openings, ensuring precise alignment with corresponding RGB phosphors. Thanks to ultra-fast scanning speeds, the human eye could not detect separate color dots, only smooth, naturally blended full-color television pictures. To maintain backward compatibility with old black and white sets, engineers redesigned the television signal encoding system. Before broadcast transmission, red, green, and blue base signals were combined to create a unified overall luminance signal. Advanced algorithms then processed color data and generated 2 independent chrominance channels. The I channel carried orange and blue tone information, while the Q channel handled green and purple color tones. As these encoded signals fluctuated, on-screen hues and shades shifted accordingly. These 2 color channels operated at a 90-degree phase difference, combining to form a complete composite chrominance signal. This chroma signal was then modulated and overlaid onto the base luminance broadcast signal. For traditional black and white television broadcasts, devices simply filtered out chrominance data, retaining clear monochrome. For modern color television receivers, luminance data was isolated and processed separately, leaving only pure chrominance information. Built-in hardware decoded the complex color signals for display. During broadcast transmission, a reference sine wave was added at the start of each signal frame. Color TVs compared incoming chroma signals to this reference wave to calculate phase offsets and differences. This allowed precise extraction of the I color channel. The chrominance signal was then shifted 90 degrees out of phase for a second round of comparison and analysis, successfully isolating the independent Q color channel. Since IQ color values followed fixed mathematical formulas, television hardware performed reverse calculations to restore original red, green, and blue signal values. These 3 primary color signals controlled the TV's 3 electron guns, ultimately producing rich, full-color on-screen visuals. Today, bulky CRT televisions have been replaced by LCD and LED screens. Yet for generations born in the 80s and 90s, these classic devices hold irreplaceable childhood memories, filled with soft, warm, nostalgic, glowing light and shadow.